When organizations first adopt Kubernetes, the architects rarely set out to build large, massive clusters. They usually start small, right-sized, and the adoption grows, right? The number of pods you have on that cluster grows, the number of nodes you have on that cluster goes, and before you know it, you have a large cluster. And at first, everything seems fine. It seems simpler. It's one thing to upgrade. It is you have controlled ingress points, maybe just a single ingress points. You have perimeter-based security, and then you can start, adding the right amount of tenancy that your clusters need. But over time, you start seeing problems. First, you might start overloading your etcd server, your Kubernetes API server. As you have more controllers and operators in the clusters, all listening on like watch operations, write operations, etc., you start overloading etcd. Or as your application's communication starts growing, you start overloading your DNS. You might have to start enforcing policies to establish tenancy between the various consumers of your clusters, where the application developers. So you might have team 1 and then team 2 and team 3. So you start writing security policies that keeps these two namespaces isolated. So you have controllers that watch and manage that. So it starts putting more burden on the security admins to keep up with all of those things in the cluster. So essentially what you're doing is you're solving for a lot of the things that you didn't need to solve for inside of the clusters, and that starts putting a lot of stress on the components. And typically, the breaking point is when you start seeing outages where a single team made a change or a single application configured something incorrectly, and it results in a cluster-wide outage, or an upgrade resulted in a cluster-wide outage. So like until things like that start forming, people usually let it grow, and then it gets to a point where you basically hit a hard block. You don't want to get to that point before you start breaking apart your clusters. But the number one reason why architects don't start breaking apart clusters is because they haven't solved the networking problem. When you start splitting your clusters apart, you need to solve for things like security for cross-cluster routing. You need to solve for observability. You need to solve for service discovery. You need to solve for DNS, etc. All of those things are exactly what a multi-cluster service mesh provides. It allows you to start right-sizing your clusters and incrementally start adopting a multi-cluster strategy. So in this very simple diagram, what I can do is start carving out segments of my cluster. These could be namespaces or could be different business units, and start creating their own clusters for them. So you're basically like splitting the cluster into multiple sections. So maybe like another cluster here, and then another cluster here. And what this allows you to do is have these two clusters owned by different teams. So you're reducing the blast radius of anything that happens in those clusters. And service mesh, specifically Istio service mesh running in a multi-cluster mode, solves for things like providing a strong identity for every single workload, regardless of where it's running, and also makes the service discovery and routing transparent, with the key being that services don't know or don't have to know where the destination service is. They should be able to call a service by a well-known host name or the Kubernetes standard host names and have a service mesh automatically, transparently redirect them securely to wherever the application is. So for that to happen, there needs to be a service mesh control plane like Istio on every single one of these clusters that are peering with one another and sharing that information between the clusters to enable that type of traffic flow. So a common architecture we see is that on the bottom here I have clusters with each one being owned by their own business units. And then on the top here, think of these as your tier 1 clusters, right? So we're kind of breaking them apart into like tier 1 and then tier 2 clusters where you run your most critical applications that need to be closest to your users in the top clusters. So let's start breaking apart these top clusters as well. So a cluster here, and another cluster here. Right. So now these tier one clusters can be distributed geographically. So that these clusters are available closest to your end users, and you have traffic coming in directly from your consumers. A service mesh can allow you to start building HA capabilities in these tier one clusters. So maybe you deploy the same instance of the service in cluster one here in US West, and maybe another one in US East, and another one in Europe, so that traffic goes to the closest destination. But if something were to happen with this service, then the in-cluster ingress can automatically fail over to the closest instance of that service in another cluster. So you now have HA, service level HA capability spread across your tier one clusters. Your tier two clusters, they don't need to have HA. For example, this could be a different business unit than this one. They all run like different sets of clusters, and they independently can choose to run multiple instances of that cluster if they want to, but they don't have to replicate services between the two. So now these tier one services capture the customer's request or your end user's request, and then they can route traffic this way, and then this knows where the final destination is, so it can go to the right destination. What this allows you to do from like a cost saving perspective is scale these clusters, right size them based on their requirements. If this particular business unit, if their application is not high demand critical workload, then they can choose to run a more cost efficient CPUs and a smaller cluster in whatever environment that is cost effective for them. Maybe this workload, this set of clusters is running your AI workload. So the CPU, the GPU memory that you choose for those clusters is going to be different than these clusters. And then your tier one clusters could be whatever allows you to distribute them geographically, closest to your end user. So this allows for a lot more flexibility, but you're not giving up on high availability. You're not giving up on security, and you should definitely not give up on observability. The last thing you should definitely solve for is observability, which is especially important in this multi-cluster architecture where your application traffic is traversing different networks, different clusters, and hopping back and forth, etc. The way to do that, just because your clusters are separate, does not mean that your observability solution has to be separate and broken. Oftentimes, the best practice is to deploy a dedicated management cluster. And this management cluster, think of it as a platform engineering owned cluster who's responsible for overseeing the rest of the entire cluster operation. So this management cluster is responsible for aggregating together metrics, traces, and other CI/CD solutions, which I'm going to talk about in a second. From an observability perspective, every cluster should have something like an OTel pipeline that is responsible for aggregating the metrics and traces from all the workloads, the control planes, etc., and shipping it to the management plane. So on the management plane, you'll run an OTel gateway that aggregates all that information together. It knows where that data came from, which cluster, which application, etc. And this management plane can either then ship that data off to your observability, your long-term storage backend, like anything that's OTel compatible, or save it locally for short-term persistence. This is where you can run your UI. So if you're running a UI, such as the Glue Mesh UI, the UI will leverage the metrics and traces collected here and give you that unified observability of how traffic is flowing exactly between your clusters. It's that service graph to help you problem determine. After observability, the last thing I want to cover is CI/CD. Ideally, your goal is that your developers that are deploying these applications don't know which cluster their application ends up on. It might be cluster 6 today. It might be need the ability to move their workload to move the workload between the clusters, run it in multiple clusters, take some clusters down for upgrade, etc. So they need that flexibility. So you need that abstraction layer in between your developers and where the application ends up on that particular day. So we'll leverage CI/CD tooling to facilitate that. So developers will take their applications, package them up as Helm charts, and store it in Git or any type of other like GitOps repository. And then that configuration gets picked up by the CI/CD pipeline. And then this is where the platform engineering team can determine where that application should be deployed to. That could be on one cluster on one day and a different cluster on a different day, like we talked about. And that gives the platform engineering team that ultimate flexibility that they need to be able to treat these clusters as cattle and right size each one of these clusters appropriately. If you're interested in learning more, contact us at solo.io.